Hi, this is Qiongxiu. I'm really glad to present the paper titled as Convex optimization-based privacy-preserving distributed average consensus in wireless sensor network. This is a joint work with Richard Heusdens and Max Christensen. I will follow this agenda to introduce our work, and let's start with the motivation. So why are we focusing on the distributed system? So in general, a centralized system is that we rely on the centralized server to take care of all the computation and processing. This kind of system is actually very vulnerable to malicious attack. Let's say if the centralized server is being hacked, then the whole system is broken. So instead of relying on any single party, the distributed network try to distribute all the computation tasks among the whole system so that even one party is being hacked, then the whole system will still be robust. And so this kind of system is more flexible. The second thing I would like to motivate is the private issue here. Here we give the daily power consumption data of our household. It doesn't look so much important or related to privacy rights. It's not your facial image, it's not your fingerprint, it's not your bank account. But actually, it turns out by using this simple power consumption data, lots of information can be revealed. For example, how many people are living in your house, and are you away from the holiday, or even are you disabled or not? So lots of personal information can be leaked from power consumption data. So we should really ring the bell and be aware that there is no real separation between your data and yourself. So we should really be careful that whenever we need to share our data. Let's go to the problem setup. I will first give the general setup of the distributed convex optimization. So the goal is that we try to jointly optimize the local objective function over the whole network and with certain constraints in this graph. Here A is the instance matrix of the graph, and B is the constraint we impose on each edge of this graph. So speaking of the average consensus, it reduced to minimize the sum of this quadratic term, and at the end we would like all the xi and xj to be the same. It means that we reached the agreement of the whole network. So there are two requirements that we should be able to achieve. The first one is, of course, we would like that at the end of the algorithm, each party should be able to achieve the average of the whole network. And the second thing is that we would like to protect our privacy. So instead of releasing our private data, let's say SI directly, we would like to first process our data. So here we denote it as GSI, and then we send out the processed data. So as long as the processed data is independent of the private data, it means that we didn't reveal anything. This can be quantified by the mutual information. There are three different kinds of existing methods. The first one is the secure multi-party combination, but it's either computationally complex or it's very heavy in communication. And the second one is a differential privacy approach. It is general, but it has a trade-off between privacy and accuracy. The last one is the correlating of insertion. It is able to give correct output, but it is not generally applicable to other problems other than average consensus. Now let's go to the proposed approach. Here we introduce the main concept of the proposed method using PDMM. PDMM is an alternative distributed optimizer, just like ADMM, but it's usually characterized with a faster convergence rate. So here is the extended augmented Lagrangian of PDMM. Let me introduce the notation here. C is the constant for controlling the convergence rate, and lambda is the introduced dual variable for the constraint. One thing to notice here is that for each edge in the graph, we introduce two dual variables, so that the dimension of this dual variable is twice the number of the edge of the network. Here, C matrix is relative to the graph instance matrix, and is given by here. The P matrix is a permutation matrix that just flips the first half and the second half of this C matrix. Having introduced all the notations, let's go to the updating functions of this PDMM. One thing to notice here is that PDMM is a broadcasting protocol. It means that we don't need to transmit this dual variable. We only need to transmit the optimization variable. So it's also why it is very efficient in communication. Now let's introduce one very important property that will be used for the privacy preservation. Let's consider two successive lambda dual variable updates. So we can see that here, every two updates of dual variable only happen in the subspace. And this subspace is constructed by the span of the C matrix and span of PC matrix. So based on this, we can decompose this lambda into two parts, into the projection, orthogonal projection into this subspace H, and the projection into its orthogonal complement. And it's already proved in PDM that this part will always converge to the optimum result. And this part will not converge. It will only be permuted at every iteration because all the updating only happen in this subspace. It will be orthogonal to this subspace, so that it will never change, but only be permuted. This is a key point that we would like to use for privacy preservation. It means that we will insert lots of noise in this subspace so that we can protect our private data. One thing to mention here that this non-convergence property of dual variable will never affect the optimization variable x from converging to the optimum value, which is the consensus, the average of the whole network. Why? Recall the Lagrange function. We can see that here PC is always orthogonal to this subspace. So that it means that no matter how much noise we insert in the subspace, it will never affect the accuracy. So this is a very nice property that we don't have any trade-off between the privacy and accuracy. Now let's go to the privacy analysis. Since based on the broadcasting protocol, since the only transmitted information is the xi, so we can always decompose this lambda into the convergent part and the non-convergent part, right? So let's see what happens if we don't have any subspace noise. It means that this part is 0. So we can see that at convergence, this xj will converge to the optimum average of the whole network, and this lambda will also converge to its optimum result. So in that sense, no matter what kind of initialization you have for these two parts, it will eventually converge to a fixed result. So it means that we can always reconstruct back what is this si here. So it means that we cannot protect our privacy if we don't have any subspace noise. So the proposed approach, we would like to insert as large as possible of the noise in this subspace so that we can mask our private data and then send out to the network. So the condition is that as long as there's one neighbor is honest. So for example, here the node 2 have 3 neighbors, 1, 3, and 4. As long as here node 3 and node 4, they are bad guy and they are malicious. But as long as he has one honest neighbor here, 1, so the information transmitted between 1 and 2, so the lambda 1, 2 here will not be known by the malicious node 3 and 4. So it means that we can use this information to protect the private data. And the conclusion is that if we have infinitely large variance of the noise, we can achieve the perfect privacy. It means that the information we send out and our private data is mutually independent. But in practice, the infinite noise is not achievable, right? So let's consider the finite noise insertion. So here we give the result that if we insert the Gaussian noise, we can always upper bound the mutual information based on this. And here is the variance ratio of the signal to the noise. We can see that if we increase the noise variance, it means that we insert more noise in the subspace. We can always decrease the mutual information. One example is that if we make the noise variance 10 times of the signal variance, we will end up 0.07 bit of information leakage. So it means that the proposed approach is practically useful even with finite noise insertion. Now, another property is that why is there always subsets? Since the subset is constructed by C and PC matrix, it's interesting to know what does it look like. Actually, the C and PC matrix can be seen as an instance matrix of a bipartite graph that is constructed by PDMM. The only difference is that here we will end up with twice the number of edges and twice the number of nodes in the network. We all know that the instance matrix of any graph is rank deficient, so there will always be non-empty subsets that we can insert noise for protecting our private data. How about ADMM? Actually, for ADMM, we also have similar result. Here is the introduced dual variable of ADMM. We can see that the updating of this dual variable only happens in the span of this M and W matrix. And again, this M and W matrix actually can be seen as an instance matrix of the bipartite graph constructed by ADMM. The only difference is that here we have n plus m number of nodes. So ADM tried to put all the edges as nodes in its bipartite graph. So again, we will end up with subsets, and we can always try to insert noise in this subsets. Now let's go to the experimental results. We randomly generate a graph, and we try to give the initialize this private data with Gaussian distribution having unit variance, and we try to initialize the dual variable with Gaussian distribution having very large variance. Here we set it as 1000. The first experimental result, we show the convergence behavior of ADM and PDMM. So we can see that here the blue line is the proposed approach, and the red line is the non-private approach. It means that we don't have any subset noise. So the blue line with the triangle marker means the amplitude of the subset noise. We can see that it always, no matter how many iterations you have, it will always keep there and never change. So this is the part that we use for protecting our privacy. And then we can see here, no matter we insert noise or not, the optimization variable x and the convergent component of this dual variable will always converge to the optimum result, regardless of the existence of subset noise or not. So this again, it validates that there's no trade-off between privacy and accuracy. And the second experimental result, we would like to compare with existing methods under different of private level. Here we use the 3 private level. One is that we don't insert any noise, and then we have 100 times of noise variance, and then the last one is we have 10,000 as the noise variance. So the differential privacy approach here is denoted by the black lines. We can see that as long as we increase the privacy level, we increase more noise in the network, then the accuracy of the whole system is compromised. And the second approach is the correlated noise insertion approach, denoted by the blue lines. We can see that it does give the correct output. It converges to the optimal result, but it slows down the convergence rate, and also in general, it converges much slower than PDMM. Now let's go to the conclusions. Here in this paper, we propose a new subset noise insertion approach based on distributed convex optimization. It is both computationally and communication efficient compared to secure multi-party commutation approach. And again, compared with the differential privacy approach, we don't have any trade-off between privacy and accuracy. And this subset noise insertion approach is generally applicable to all the convex problem, not only to the average consensus problem. And the one limitation of the proposed approach is that we need one honest neighbor, which is not required in the differential privacy approach. All right, thanks a lot.